Hello, everyone, and welcome back to our channel. Today, we're diving deep into a fascinating and mind-bending topic that bridges the gap between quantum mechanics and the very essence of our consciousness. This is the observer effect, reality and consciousness. In our previous videos, we've explored some truly captivating subjects. We discussed how quantum techniques can unlock the subconscious mind, revealing profound insights and hidden potentials. We delved into the multiverse theory, where parallel universes coexist, each shaped by different possibilities and outcomes. And we ventured into the realms of string theory and extra dimensions, uncovering the fundamental nature of the universe. Today, we're going to build on these concepts and delve into the mysterious and profound observer effect. This phenomenon has profound implications for our understanding of reality and consciousness, and it's a topic that has fascinated scientists, philosophers, and mystics alike. So, let's embark on this journey together and explore the profound implications of the observer effect on our understanding of reality and consciousness. To understand the observer effect, we first need to dive into the world of quantum mechanics. Quantum mechanics is a branch of physics that deals with the behavior of particles at the smallest scales, such as atoms and subatomic particles. It's a world that defies our everyday intuition and operates under rules that are fundamentally different from the classical physics we experience in our daily lives. One of the most famous experiments in quantum mechanics that illustrates the observer effect is the double-slit experiment. Imagine you have a barrier with two slits and a screen behind it. If you shoot particles, like electrons, one at a time through the slits, you would expect them to hit the screen directly behind each slit, creating two distinct lines. But in the quantum world, something extraordinary happens. When not observed, these particles act like waves and create an interference pattern on the screen, a series of light and dark bands. This pattern suggests that each particle goes through both slits simultaneously and interferes with itself. However, when we place a detector to observe which slit the particle goes through, the interference pattern disappears. The particles behave like particles again, hitting the screen in two distinct lines behind each slit. This shift from a wave-like interference pattern to particle-like behavior when observed is what we call the observer effect. The mere act of observing changes the outcome of the experiment. This raises profound questions about the nature of reality and the role of the observer. How can simply observing something change its behavior? What does this tell us about the nature of particles and waves, and the fundamental structure of reality itself? To explore these questions, we need to consider the relationship between observation and consciousness. Some scientists and philosophers propose that consciousness itself plays a crucial role in the observer effect. One prominent figure in this discussion is Niels Bohr, one of the founding fathers of quantum mechanics. Bohr suggested that the act of measurement collapses a quantum system from a superposition of states into a single state. In other words, before observation, a particle exists in multiple states at once, a superposition. But the act of measurement, the conscious act of observing, forces the particle to choose a single state. This idea has profound implications for our understanding of reality and consciousness. It suggests that consciousness might be deeply intertwined with the fabric of reality. Another key figure in this discussion is Eugene Wigner, a physicist who took Bohr's ideas a step further. Wigner proposed that consciousness itself is necessary to collapse the wave function. In other words, without a conscious observer, the universe would remain in a state of superposition, with all possible outcomes existing simultaneously. This view, often referred to as the Wigner's friend thought experiment, challenges our conventional understanding of reality. It suggests that consciousness is not just a passive observer of the universe, but an active participant in shaping it. These ideas have sparked intense debate and ongoing research in the scientific community. While some scientists embrace the idea that consciousness plays a crucial role in the observer effect, others are more skeptical. Critics argue that the observer effect can be explained without invoking consciousness. They suggest that any interaction with the environment, not just conscious observation, can collapse the wave function. This perspective, known as decoherence, proposes that particles interact with their surroundings in ways that cause the wave function to collapse. Decoherence offers a way to explain the observer effect without requiring consciousness to play a central role. Yet, the debate continues, with ongoing research and experiments aimed at uncovering the true nature of the observer effect and its implications for reality and consciousness. As we delve deeper into these ideas, we encounter profound philosophical questions. Does reality exist independently of observation? If observation shapes reality, what does that mean for our understanding of the universe and our place in it? One philosophical perspective that grapples with these questions is idealism. Idealism suggests that reality is fundamentally mental or spiritual in nature. In this view, consciousness is not just a part of the universe, but the foundation of it. The observer effect supports this perspective by suggesting that consciousness plays a crucial role in shaping reality. On the other hand, materialism argues that reality is fundamentally physical and exists independently of consciousness. Materialists argue that the observer effect can be explained through physical interactions and does not require consciousness to play a central role. These philosophical debates highlight the profound implications of the observer effect for our understanding of reality and consciousness. As we explore these ideas, we also encounter practical implications for our daily lives. If observation shapes reality, how might our perceptions and beliefs influence the world around us? Could our conscious awareness and intention play a role in shaping our experiences and outcomes? One practical application of these ideas is the practice of mindfulness. Mindfulness encourages us to observe our thoughts and experiences without judgment. By becoming aware of our thoughts and perceptions, we can begin to see how they shape our reality. This awareness can empower us to make conscious choices that align with our intentions and goals. Another practical application is the practice of visualization. Visualization involves creating a mental image of a desired outcome. By focusing our conscious awareness on this image, we can begin to shape our reality in alignment with our intentions. These practices suggest that our conscious awareness and intention can play a powerful role in shaping our reality. As we explore the observer effect and its implications, we also encounter fascinating thought experiments. One such thought experiment is Schrödinger's cat. In this experiment, a cat is placed in a box with a vial of poison that will be released if a radioactive particle decays. According to quantum mechanics, the particle is in a superposition of decayed and not decayed states until observed. This means the cat is both alive and dead until someone opens the box and observes it. This thought experiment illustrates the paradoxes and mysteries of quantum mechanics and the observer effect. It challenges our understanding of reality and the role of observation. Another thought experiment is the many worlds interpretation. This interpretation suggests that every possible outcome of a quantum event actually occurs, each in its own parallel universe. In this view, the observer effect creates a branching of realities, with each branch representing a different outcome. This interpretation offers a fascinating perspective on the nature of reality and the role of observation. As we explore these thought experiments, we begin to see the profound and far-reaching implications of the observer effect. It challenges our conventional understanding of reality and opens up new possibilities for understanding consciousness and the universe. As we conclude our exploration of the observer effect, let's summarize the key points we've discussed. The observer effect suggests that the act of observation changes the behavior of particles, collapsing them from a superposition of states into a single state. This phenomenon raises profound questions about the nature of reality and the role of consciousness. Some scientists and philosophers propose that consciousness itself plays a crucial role in the observer effect. Others argue that the observer effect can be explained through physical interactions without requiring consciousness. These debates highlight the profound implications of the observer effect for our understanding of reality and consciousness. As we explore these ideas, we also encounter practical implications for our daily lives, including practices like mindfulness and visualization. And we encounter fascinating thought experiments that challenge our understanding of reality and open up new possibilities for understanding consciousness and the universe. We delved into theories linking the observer effect to consciousness, with insights from Niels Bohr and Eugene Wigner. We also touched on the philosophical and practical implications of these ideas. Now, let's dive even deeper into this fascinating topic. In this part, we'll explore more complex theories and thought experiments, as well as the ongoing scientific debates surrounding the observer effect. We'll also consider the broader implications for our understanding of the universe and our place within it. Let's begin by exploring some advanced concepts in quantum mechanics that are closely related to the observer effect. One such concept is quantum entanglement. Entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle instantly influences the state of another, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance. This phenomenon challenges our understanding of space and time and has profound implications for the nature of reality. In an entangled system, the measurement of one particle's state immediately determines the state of its entangled partner. This suggests that the act of observation is not just a local event but has non-local effects. Entanglement raises questions about the nature of information and how it is transmitted across space. It suggests that reality is deeply interconnected in ways that transcend our classical understanding of the physical world. Another advanced concept is quantum superposition. Superposition is the idea that a particle can exist in multiple states simultaneously until it is observed. This concept is fundamental to quantum mechanics and underlies the observer effect. In a superposition, a particle exists in a combination of all its possible states. The act of observation collapses the superposition into a single state. This collapse is what we observe as the outcome of a quantum event. The concept of superposition challenges our classical understanding of reality. It suggests that reality is not fixed but is a dynamic interplay of possibilities. The observer effect reveals that our conscious awareness plays a crucial role in shaping which of these possibilities becomes our experienced reality. As we delve deeper into these advanced concepts, we encounter more thought experiments that illustrate the mysteries of quantum mechanics and the observer effect. One such thought experiment is the delayed choice experiment. This experiment, proposed by physicist John Archibald Wheeler, explores the idea that choices made in the present can influence events in the past. In the delayed choice experiment, particles are sent through a double-slit apparatus, similar to the original double-slit experiment. However, the decision to observe which slit the particle goes through is made after the particle has passed through the slits but before it hits the screen. Surprisingly, the results suggest that the particle's behavior changes retroactively based on the delayed choice. This thought experiment challenges our understanding of time and causality. It suggests that the act of observation can influence not only the present and future but also the past. The delayed choice experiment reveals the deep and complex relationship between observation, time, and reality. Another thought experiment is quantum teleportation. Quantum teleportation involves transferring the state of a particle instantaneously from one location to another without physically moving the particle. This process relies on quantum entanglement and the observer effect. In quantum teleportation, the state of an entangled particle is transferred to a distant particle through the act of measurement. This process reveals the non-local nature of quantum information and the role of observation in transferring information across space. Quantum teleportation has practical applications in developing secure communication technologies and quantum computing. It also challenges our classical understanding of space and information transfer. These thought experiments illustrate the profound and far-reaching implications of the observer effect. They reveal that observation is not just a passive act but an active participant in shaping reality. As we explore these advanced concepts and thought experiments, we also encounter ongoing scientific debates about the nature of the observer effect. One such debate centers around the role of consciousness in the observer effect. While some scientists propose that consciousness plays a crucial role in collapsing the wave function, others argue that the observer effect can be explained without invoking consciousness. Decoherence theory offers an alternative explanation. Decoherence suggests that the interaction of particles with their environment causes the wave function to collapse. This process does not require a conscious observer. Instead, it relies on the physical interactions between particles and their surroundings. Decoherence provides a way to explain the observer effect within the framework of classical physics. It suggests that the appearance of a definite state arises from the complex interactions of particles with their environment. This perspective challenges the idea that consciousness is necessary to collapse the wave function. Another ongoing debate concerns the interpretation of quantum mechanics. There are multiple interpretations of quantum mechanics, each offering different perspectives on the observer effect and the nature of reality. One interpretation is the Copenhagen interpretation. This interpretation, proposed by Niels Bohr and Werner Heisenberg, suggests that the act of measurement collapses the wave function into a single state. The Copenhagen interpretation emphasizes the role of observation and measurement in shaping reality. It suggests that reality does not exist independently of our observations. Another interpretation is the many worlds interpretation. These thought experiments illustrate the profound and far-reaching implications of the observer effect. They reveal that observation is not just a passive act but an active participant in shaping reality. As we explore these advanced concepts and thought experiments, we also encounter ongoing scientific debates about the nature of the observer effect. One such debate centers around the role of consciousness in the observer effect. While some scientists propose that consciousness plays a crucial role in collapsing the wave function, others argue that the observer effect can be explained without invoking consciousness. Decoherence theory offers an alternative explanation. Decoherence suggests that the interaction of particles with their environment causes the wave function to collapse. This process does not require a conscious observer. Instead, it relies on the physical interactions between particles and their surroundings. Decoherence provides a way to explain the observer effect within the framework of classical physics. It suggests that the appearance of a definite state arises from the complex interactions of particles with their environment. This perspective challenges the idea that consciousness is necessary to collapse the wave function. Another ongoing debate concerns the interpretation of quantum mechanics. There are multiple interpretations of quantum mechanics, each offering different perspectives on the observer effect and the nature of reality. One interpretation is the Copenhagen interpretation. This interpretation, proposed by Niels Bohr and Werner Heisenberg, suggests that the act of measurement collapses the wave function into a single state. The Copenhagen interpretation emphasizes the role of observation and measurement in shaping reality. It suggests that reality does not exist independently of our observations. Another interpretation is the many worlds interpretation.